Good morning, this is Dan with Bit by Bit Computing. Today I want to do a quick video review of my model, which is a little boy Hiroshima atomic bomb. Normally when I do my scale aircraft and models, we use injection molded kits and resin kits. This time around we decided to do a 100% 3D print. Let's see how it came out. Basically what I did was I went online to cgtrader.com and I purchased plans for essentially it's a 1/8 scale atomic bomb. The model's from Anthony Williams and it is sort of copyrighted. It is his plans, but they are available for public use. The model we printed consisted of 100 PLA parts, and we printed everything with no supports. All the parts are slotted and friction fitted for precise assembly. We used a printer and sanded some custom slices on it. I did wire it with 2 LEDs and it features a fully movable target. The airbrush work was done with an Iwata HPC Custom and Tamiya and Vallejo acrylics. Now the actual atomic bomb is 9,700 pounds and it's about 10 feet long. The explosive yield is 15 kilotons, but the unique fact is only 1.3% of it actually fissioned, which is about it's fairly small. The total uranium weight was 140 pounds. The blast would have been a whole lot more damaging if more of it would have fissioned. The absorbed dose at the hypocenter was 240 grays, and it falls off to 10 grays 1 mile out. For comparison, a 5 gray is a fatal dose. Your average Houston background is about 0.006 grays per year. The effects of the radiation sort of vary depending on the structures and your distance from it. The kind of radiation. You had alpha, beta, and gamma. A little history on the bomb. The bomb components were delivered to Tinian Island by the cruiser USS Indy under deep secrecy. July 30th, 1945, she was torpedoed by a Japanese sub, and 884 of her 1,200 crew members lost their lives, many of them due to sharks. Due to the top secrecy of the mission, she wasn't reported missing for a few days later. That's why the death toll was so high. The ironic thing is the Japanese sub actually saw it on the way to the island, but decided not to attack it. If it would have sank it then, there would have been no atomic bomb. It's a little ironic twist of fate there. The Enola Gay dropped L11, which is the 11th casing, on August 6, 1945. One thing that I did, purchased and modified a miniature Geiger counter, and I'm going to mount that eventually inside of the cutaway in the front. It is a fully functioning Geiger counter. Let me run the video. This is a video of it. The whole thing's on a circuit board. It's a Russian SBM tube. It's very sensitive to beta and gammas. Runs off of a 9 volt. You have a high voltage section, you have a counter, you have a speaker, you have an LED. What I have mounted on the toothpick is a radium watch hand. I'm using that as a gamma source because the background counts are pretty low here in Texas. But you can see the light flashing. If you turn up the audio, you can hear it click. Now this whole thing I'll eventually airbrush and I'll put inside of the model itself. It's about $40 for the kit. Okay, what do the clicks or the counts mean? The sievert's the unit for absorbed dose. 1 sievert is 1,000 millisieverts, or 1 million micro sieverts. The micro sieverts is a pretty common unit. We're exposed to radiation from outer space, radon gas decay, and medical devices. This background is measured in units called millisieverts. The average dose per person from all sources is about 10 millisieverts. 'sieverts. It is higher if you do a whole lot of medical imaging. The 1 million microsieverts is about 1,000 millisieverts, or 1 million micro sieverts. This background is measured in units called millisieverts. The average dose per person from all sources is about 10 millisieverts. It is higher if you do a whole lot of medical imaging. For comparison, 8 million microsieverts is fatal. In the Chernobyl reactor hall, the dose was 50 million microsieverts. Time to fatal exposure at this count is 22 seconds. So how do we actually use the Geiger counter to figure out your background counts? Basically, you count how many clicks you hear in a minute, and you plug it into this formula. So let's say if I got 200 clicks a minute, it would be 200 times 0.005. That comes out to 1 microsievert per hour for this tube. 500 clicks, 500 flashes would be 500 times 0.005. The sensitivity factor is calculated by the manufacturer, and it's printed on the spec sheet when you buy the Geiger counter. I got a background in industrial hygiene, chemistry, and I did some field work where I had to be the radiation safety officer for the company. So it's, and they had a course on it. Here's a picture of the actual board, and there's the schematic. Okay, let's get to the actual model. This is a picture from the outside. It's airbrushed in green, some yellow, some black, some stainless colors are in there too. On the front end of it, I custom made these barometer sensors and the lock nuts on the real thing. Here's a picture of the actual atomic bomb in black and white. There aren't any color photographs of the real thing. As you can see, the outside casing's L11. They made, I think, 12 casings for it. You got these fusing safety wires, lifting lug. These are the antennas for the altimeters, the tail section. Here are your barometric pressure sensors and the lock nut. If you take a look at it, you can see the machining mark in the steel. It's fairly well replicated on the 3D print. The nose, you can see the sensors. Here you can really see the machining on the casing itself. Here's a view of the full cutaway. The atomic bomb basically has 4 sections. You have the bottom of the barrel where you have the gunpowder charges. Here you have the projectile pusher and the uranium-235 target ring. You have a gun barrel. You got a bunch of electronics, altimeter, firing mechanisms for the charge. I put a push button in to run the LEDs. And there's a battery box. There's a real battery box on the real thing. And this is the business end of the bomb. Basically, when you detonate this charge, this uranium-235 ring accelerates down the barrel, forms a critical mass, goes boom. You have a steel and a tungsten in the brick section. It acts as a neutron reflector. And you have a basically a backstop in here to keep it from blowing through. Here's the cart that really isn't like the real one. Tail section. The LEDs are green and blue. Later on I'll post a video of the lights. Here are the Yagi antennas for the radar altimeters. Let's take a look at the close-up of each section. This is a close-up of the real atomic bomb. On the model that was bought off the internet for the plans, the cutaways on the other side. The bomb is symmetric. You can put the electronics on either side or both sides, and you can have the cutaway on both sides. It's just that for this model, the way it's keyed, the electronics bay is exposed on the other side. It's just a little minor technical difference, but it's really not that big of a deal. Here's a close-up of the front end. The LEDs behind the uranium-235 target rings. This is a duro alloy. These are tungsten bricks. It acts as a neutron reflector. This is a tungsten backstop that keeps the rings from blowing through the end of the bomb. The whole idea is for a critical mass you have to assemble it extremely fast, and you have to really squash the mass down, so they put this tungsten backstop in to keep it from pushing through. Remember, this bomb design was never tested. They were pretty sure that the gun assembly version would work. Only the implosion bomb was tested at Trinity. The mathematics and the physics are a lot more complicated on the implosion sequence than the gun device here. As you can see, I did a pretty extensive dry brushing and airbrush work here. All this detail is molded into one piece. I didn't have to add the hex nuts. Everything's friction fitted with minimal amount of super glue. Now the problem with the PLA print is if you try to sand out the imperfections to make a contest piece, it really doesn't work too well. You almost have to do the whole bomb in a urethane resin mold printer, SLA, but my guess is it would be extremely expensive to do a resin print at this scale. But you can see the details pretty fine. You can actually see this lip here. This lip is actually on the real bomb itself. When the cover goes on, there's another layer of steel that forms a layer that occupies the space. So this is not a defect. That's the way it is on the real thing. Here's another look at the front end from a different perspective. These nuts are on the real bomb itself. I use S&J metallizer and silver rub and buff for the gun barrel part. I airbrushed the whole thing in gloss black lacquer. While it was still wet and tacky, I wet sanded and I took steel wool to it, and that gave it this really worn down, rough look to it. You can see the scratches. You can see the silver color coming through the dark black. I think it really looks good visually. This is a close-up. Here the two targets are compressed into one. This is a stage where it goes boom. You got a neutron initiator here, and you got the two cores assembled. Here's a section of the electronics bay. It's a little rough. 9-volt battery goes up here. I rigged up the push button, got electronic bays. On the opposite side of the bomb, you can mount the same components. There's a company called ONZY. They make these resin switches, knobs, and buttons. I'm fixing to order some once the virus embargo is lifted. So I'll probably eventually cut these off and use that resin aftermarket kit set for that. It'll be a lot more realistic looking because I can sand out these gauges and actually put actual switches and knobs in place of these aircraft panels that look a little phony. That'll make it look a little bit more realistic. The target goes in this barrel all the way down to the end. Here's a picture of the back end of the bomb. These are the gunpowder sacks. There are naval deck gun charges. The primer, it's cordite. Basically, it lights it, forces the projectile down the barrel. It's a very simple design. These are the electrical conduits. On the real bomb, these are hollow. So in a future print, I make these hollow so I can run my wires through these conduits. Cleaned up a little bit. This is the pusher projectile, and this is the uranium-235 rings. As long as they're apart, it's a subcritical mass. When you assemble it, it goes supercritical and goes boom. This bomb really didn't have any safety features except for the fuse wire lockouts. Anything that detonates these charges in the back will cause the bomb to go off. They're worried about shock, high humidity, temperature, an accidental spark, friction, aging of the gunpowder. It really wasn't a safe design. They did put a thin metal wall up in here to keep the projectile from accidentally being pushed through and not being explosively pushed through. But in theory, if anyone were to spark this or get this hot or set it off, the bomb would go off. There are no safety features that prevent that. That's why they assembled it at 10 yen and quickly loaded the Enola Gay and said, bye bye, it's time to go. You don't want this arm bomb just sitting around. Design's not totally safe. Here's a close-up. At the back end, you can see where I metallized it. Different airbrush shades for the projectile pusher, the uranium-235. There's a lot of color photographs of what the uranium-235 looks like. So I can get a fairly accurate color. That's that rub and buff. Finally, this is the back section. This is the LED. This is a cutout of the canvas sacks that had the powder charge in it. Again, these are from a naval deck gun. There's nothing high-tech about it. Extremely dense steel. It's a gun barrel. Here's a modified Photoshop image of the cutaway. I gave it a little creative license. I did a little blur effect. I gave it a little warm glow filter to it. Now the tail is a 3D print. That's one piece. Here's a video. The tail print took 36 hours at the highest resolution. When the print is done, all I had to do is knock off the excess filament, do a little wet sanding, and it's finished. It is 90 degrees true. The printer does a pretty accurate job of it. If you look at it, the printer actually prints the cutouts and the fins. It's back to the Geiger counter. Essentially, that's it for the little boy. If anyone has any questions, you can find me on my Facebook page, Dan Rutman, R-U-T-M-A-N, or you can go to Bit by Bit Computing and look me up there. Hope you enjoyed it. If you had any questions, feel free to chime in. Have a good day.